Consider the set of data points in the xy plane denoted by the pink dots and a line which we are trying to adjust such that its distance, which I am denoting with orange line segments, is minimum. How will we tune the parameters of this line which makes the distance from each point minimum? If we try to minimize the distance of a line from a one point, then we are moving away from another point. How will you tune this line, the parameters of this line, which makes the less error? So welcome to the lecture on least square regression. For a simpler case, we are trying to fit a line, but for the curve may be as much complicated as we want, subject to the shape of the data. So how will we tune the parameters of this line which will do the minimum error? If I plot the errors of this line with the fitted line, then we can see how the distance is varying from each point to the line. So our goal here is to identify a line, tune the parameters of this line, which will make the less error, which means that the length of these line segments is minimum, as much possible as we can minimize. So the question is, how can you do this? So this is what we will do with the help of the least square technique, a curve fitting technique where we try to minimize these length of these line segments from these points and a selected mathematical model, which in this case is a line. So this line curve need not be a line, it may be some highly nonlinear curve, which we can see. So how will we tune this? That we will see with the least square method. So what is least square method? For that, before that, we will see what curve fitting is. So we have a data from the experiment and we try to estimate the relationship between this dependent variable and my independent variable. So this is the scatter plot of my data, let's say, and I'm asking you fit a possible relationship, mathematically try to explain the relationship between my dependent and my independent variable. Now this data, which kind of shows the trend of increasing, need not to lie on a straight line, but sometimes our data contains noise with which there is experimental error in the data, which leads to the points to move away from the line or some other curve. So a simple possible case can be if we try to join these points with the line segments. But will this be a good estimate of the trend our data is showing? So that we can see by comparing how much error it's doing. So if we do this way, then we are doing a zero error. But is this mathematical model, which I am saying joining the points with the line segments, but is this a good choice for this data? You may fit some arbitrary curve which is trying to explain that, but is this better than just fitting a line segment? So how can you compare these two things? This is what we will do with the curve fitting technique. So there are infinite number of possible ways to fit a curve, but how do we choose the curve which is doing optimal, which is doing less error, and how do you obtain the parameters of that curve uniquely? So the question first we ask, why do we need to fit a curve to this data set? So for that, we did the experiment with few number of times and we want to predict next time without actually performing the experiment. That's called doing the predictions. We try to estimate the possible relationship between the variables. We may not be knowing the relationship between our input and output variable. So how our dependent variable and our independent variable in the experiment, how they are related, how one is influencing another. So sometimes our goal is to try to check the possible relationship, how one is doing affecting another. There are different types of curve fitting techniques. One is the least square, which we will be discussing in this lecture. Another is interpolation technique. In the least square method, as I shown you, that we try to minimize the error, fitting the curves which is doing less error. But in the interpolation techniques, we are not doing any kind of error. We are exactly passing through those points. But sometimes there's a noise in the data, then the interpolation techniques gives wrong results, or results which are not close to the true results, true relation between the variables. So in those cases, we will go for the least square method. What are its applications? The important question may be, why do we fit the curve, but what are its possible applications? The applications are to make inferences over the unseen data. So now you have some unseen data, which means you are trying to predict how your experimental work is going to perform in the future, or the in between the points which are you have measured between 2 point at two instances, you have measured the experimental values. Now you want to predict what will be the value of your dependent variable when you are having independent variable between those 2 points. So there are many applications in the machine learning context. Many machine learning tasks can be formulated as a curve fitting task, be it a regression or a classification task. In the classification task, we are trying to find an optimal curve which is separating between the two curves, which is helping us to decide how you can separate two data sets or two kinds of items. So curve fitting techniques are very important, and in machine learning, where we don't have the direct methods, then we go for the iterative methods, the gradient descent technique. That's not a part of this lecture. We will see what least square method is. So the least square says, in the simpler case, we are trying to fit a line to a set of data points, and we are trying to minimize the error, which means the length of these points from this curve. Now, if I mathematically formulate this problem, then distance of a point from this point line, it can be written in the form of the absolute difference. Yi is my actual point, and I am trying to minimize its distance from my approximated value, which is the line which I denote with the yi hat. So this is my point, and I am trying to minimize distance from the line. Now, if I check this function, this is the absolute value function, and we know that we cannot use the rules of calculus for this kind of functions. So instead of using the absolute value function, I am trying to minimize the area of these squares. Now I have, instead of minimizing the length of the line, I am drawing the squares and whose edge length is exactly the length of the line. So this is how we write in mathematical formula. So I will be saying I have a loss function, which is the total error all these points this line is making with respect to all these points. So I am summing all those errors, area of the squares of all those at all those points. Now in this case, we are fitting just a line. So the parameters of the line are its slope, which we denote with m, and intercept, denoted by c. So these are the two parameters of our line. If I try to tune these parameters by changing the slope or by changing the intercept, you can see the length of these points, distance of these points from the line is varying. So we have to uniquely identify this line, these parameters of the line, which is describing it and which is doing the least error. So I have formulated my problem as an optimization problem. I'm fitting the mathematical model here, a straight line, and I'm calculating the value of the predicted value of at each input variable xi. Then I can compute the distance of these yi's predicted values and the actual values. So this is the actual value, and this is my predicted value, which comes from the mathematical model. So this is how we define it as a mathematical problem. Now our goal here is to minimize this. So now we can use the rules of the calculus. So there need not be a straight line like y is equal to mx. You can go for the quadratic fit, cubic fit. Let's see how we can do that to the data set we are having with us. So if I try to fit a quadratic curve or some other model to this data set, so this is our linear fit. And if I do go for the quadratic fit, we can go for the cubic or quartic or exponential, and so many models we can go for. Now there's also a task where you have to decide among all these points which one among all these possible models, which one is the better model. So not not all models are equal predictions doing. All models are actually wrong, but some are useful. So we are trying to estimate the relationship. This is about estimating. So how can you compare different models with respect to each other? So you can have different families of models depending on which one fits better. You can have exponential, logarithmic, sinusoidal, all these kinds of things. Let's go for the linear fit. So in the linear fit, what we are doing is we are fitting a line y is equal to mx plus c. Now our loss function will be a function of two parameters m and c. Our goal here is to obtain the optimal values of m and c, which means try to tune the parameters m and c such that the area of the squares or the distance of these points from the line are minimum. The distance is minimum from all these points together, considered together. Now we know that this is a two variable problem, calculus of two variable problem, where you have to find the minima of a function, two variable function. Now we know that for minima our gradient should be maxima or minima, our gradient should be 0. That's why I calculate the partial derivative of this function, loss function, with respect to my slope, and partial derivative with respect to the intercept. At optimal points or the critical points, these these slopes should go to 0. If you solve these two derivatives, you will get a unique value of m and c in terms of your data independent variable and your independent variable. But our fit to the data need not be a linear fit. We can have some non-linear curve to the data. So suppose this blue dots are my data, and I'm trying to fit a non-linear curve, in this case kind of sinusoidal data. So we can do this kind of thing with the same technique, provided I am having the model. Let's say y is equal to a times sine of bx plus c. So if I go for this model, then I have to take the derivative with respect to three unknowns. So that's how you can go for the nonlinear fit. But among all these possible curves, let's say I have this data set, and I have fitted a straight line, quadratic line, and some other curve. So which one is better fitted? Now this line is clearly not capturing the trend of the data, actual trend of the data, and this is doing better relative to just a simple line. What about this? this is some other model. How can you compare which one is actually fitted better? Now, for few data points, the job may look easier, or we can do it visually. But what if you have a millions of data points with you? How can you do for that? So we need to define a measure of goodness of fit that we call in the statistics as R square value. So what R square is doing, it's measuring the proportion of variance in the dependent variable that is explained by the independent variable. So it's trying to explain how much variation is captured by the model, how much is left. So it measures how well the regression line, a simple line or some other curve approximates your actual data. R square is defined as 1 minus RSS by TSS, where RSS is the variation left. Total variation in RSS is a residual sum of squares. You are summing of all the residual. This is the difference between the actual value and the predicted value, and squares of that summing all these at all points. This is called the residual sum of squares. And we have TSS, total sum of squares, which means the total variation in the data, or the variance. So this is R square is not always a good measure, but this gives some idea. There are cases where we have a very good value of R square close to 1. Here in the case of regression line, you will get your values of R square between 0 and 1. Closer to 1 means the model is fitted better, close to 0 which means model is performing poor. But sometimes we get a very good value of R square, but still our model is not a better model. Reason is the overfitting. Our model is trying to do overfitting, which means, let's say in this case, we have a quartic data, we have fitted a quartic curve, and it's trying to fit itself with the data, with respect to the data. Now if this is my quartic curve with respect to these data points, and if I go for the linear regression line, is it's better performing as compared to the quartic. That we can also see with the help of R square. So R square here is actually better for the case of quartic, and for the case of linear we are getting less value of R square, but still we will go for the linear case because it's trying to better approximate the data. This is the case of overfitting. In the case of quartic, the fourth degree polynomial, it's doing the overfitting. So that we have to be very careful at the time of fitting the curves. We may also have the cases where our model is performing very poor. That's called the underfitting. So what about higher dimensions? Now this was a line or a curve which is passing through which is trying to adjust itself with respect to the data. Now what if we have more than two variables, two independent variables, let's say x1 and x2, and our dependent variable is y. If we go for the linear approximation, y is equal to a x1 plus b x2 plus c. Now this is a linear relationship. In the high dimensional space, it will be in the three-dimensional space now, it will be a plane. So beyond the three, we call the hyperplanes. So in this case, we are trying to minimize the distance of the points with respect to the plane in a three-dimensional space. Now we may have a non-linear relationship. In those cases, we will get some other kind of surface, but with the problem remains same. So now we will go for the curve fitting in Python, how you can do this curve fitting in Python. We are trying to do the curve fitting over the simulated data. So I have a library called the draw data with me. With that, I will try to simulate some data and make models that will fit to that data. So I'm calling my library. Let's run this now. Now let's try to make some data set with the by dragging the mouse. So let's say this is my kind of data set. Our goal here is to try to estimate or try to fit a model which will explain this data set. So I will store this data set as a data frame, pandas, and now I am separating my dependent and independent variables from the data set, calling some inbuilt libraries for plotting and curve fitting. Now, if I go for the simple linear curve fitting case, this is the line which we are trying to fit, but this line is not the optimal, as we can see from the residuals. Also, residuals are showing there is kind of pattern left which is not captured by the model. And also with respect to the R square, although it's about 78%, but still our model needs some improvements. Let's go for some other kind of model. So I'm defining my model as here you can change your model. Now I will be defining a model of order 2, which means a quadratic model. Now let's try to do the curve fitting. So this is my curve fitting with respect to the second model. It's kind of performing the same, but yeah, we have not taken the square. Now let's take again. Now there is some curve kind of bent in the curve. Still, we got 80% R square value, but the pattern in the data is still left. So our model needs further improvements. Let's go for a cubic curve. Uh, Cubic curve d into x to the power 3 I am adding to my existing model. Yeah, here you can see how our model fitted well to this data. And if we look at the residuals, there is kind of white noise left in the data. You can go for higher order values, but they will lead to the overfitting. So in this case, cubic is best fitted. And if we look at the R square value, I'm getting R square value of 93. 0.93, which is 93% of the variation is 93% is as a measure of goodness of fit. So this is how you can do it in Python, where you can write your own programs and you can fit models, you can update your models, you can upgrade your models, and you can check the goodness of fit of the model. Now in this case we were doing on a simulated data, but in the real life you will be getting a data which may not have this kind of structure. So in those cases you need to be very careful what kind of model can be fitted over this data set. Thank you.